Hello, everyone. Welcome to PyData Global. We're excited to have you join us. Feel free to use the chat to connect with fellow attendees and share your thoughts during the session. If you have any questions, please post them in the Q&A tab, and we'll address them at the end, time permitting. But now it's my pleasure to introduce Eyal Gruss. He'll be presenting his talk, Let Our Optima Combine. Let's give a warm welcome to Eyal.
Thank you very much for having me. So I'm Eyal Gruss. I'm a machine learning researcher working as a freelancer. I'm also an artist doing stuff with code, with media and text, and I teach computational creativity at the Holon Institute of Technology. So my talk today is about combinatorial optimization. And in combinatorial optimization, we will want to discuss problems where we need to do some kind of selection, matching, assignment, arrangement. And in these problems, our variables will be discrete variables, or it can be approximated as discrete. We will have different kinds of constraints for which we will want to find feasible solutions. Constraints which may also be global, complex, nonlinear. Optionally, we can have an objective function or several objectives which we will want to maximize or minimize. And our solutions may have a lot of different combinations of the values of these variables, probably too many for us to enumerate them all, so we need to do something smarter. So just to give you the vibe of the type of problems we're discussing, mainly we'll talk about more generally about constraint satisfaction. The canonical problem here is you have a Boolean proposition and you want to check if it's satisfiable. We can talk about problems from the puzzle domain or recreational math, where you have crosswords or a Sudoku you want to solve, crypto arithmetics, where you want to find the mapping between some letters and numbers and solve the riddle or the cipher. The 8 queens problem, for example, you want to put these chess pieces on a board so nobody attacks each other. We can discuss more real-world constraint satisfaction problems, like solving software dependencies, as you may know from doing conda install, doing automatic type inference, and most importantly, you may have a wedding, you want to arrange the seating. Some people must sit together and some people must sit apart. We can also go into more specific domains. We can discuss packing or the dual problem of covering, where you have some assets or resources which you want to allocate to beans. A very real world and important problem is of scheduling. You may have employees which you want to put into shifts. You may have a manufacturing floor with different machines that can do different tasks in different orders, and you want to set it all up. You may want to do a school timetable, so you have these like classes, rooms, teachers, subjects, hours, maybe a budget, and you want to make everything work together. So these are like more specific, maybe subtypes of constraint satisfaction. And lastly, we also have routing or network flow problems. Known example here is the traveling salesperson, where you want to go through each city only once and the shortest path. And probably specifically for routing, you would want to use a dedicated solver, although you can also try the more general methods as we will discuss today. I will talk today about OTools. This is Google's software suite, open source for operations research. It's probably one of the most popular solutions on GitHub, and also the support is amazing. Like they fix problems very, very quickly. And this package is like also really good and really fast. So this is like the MiniZinc challenge, and since the solver that we will talk about today started in 2018, the all tools CPSAT won virtually all of these categories for combinatorial optimization. So it's a really good package. And we will discuss today this solver, which is called a CPSAT, CP for constraint programming, and SAT for satisfiability. And in these kinds of CPSAT problems, the method uses an encoding which is called order encoding. Essentially, CPSAT will reformulate the problem as into a logic problem. You can think about it as a problem in logic. If you have, for example, integer variables, I, which can take an integer value, is 1, 2, or 3, it will be transformed into a set of Boolean variables, checking if I is equal to 1, equal to 2, equal to 3, also if I is less or equal to 2, less or equal to 3. And this kind of representation allows the Boolean to capture also the order information of the integers. And you don't have to worry about all of this because it's done behind the scenes automatically and lazily, so it's efficient. Why use CPSAT? So before I found out about this option, I would do heuristic optimization, which is very fun to think about, but the issue is that you're not assured that you will find all the solutions or the best solutions. And also you don't know if you found all solutions or the best solutions. Another way to go about this is to do exhaustive search. Here you will need to use different kinds of handcrafted optimizations because otherwise there are too many solutions to enumerate. And the issue is that these optimizations are per domain. They can be hard. They can be error prone from the algorithmic point of view. You need code which is more complex and therefore also more error prone, and probably it will still be too slow. So CPSAT can solve all of these problems. CPSAT, and this is like a very gross simplification, but it exhausts the search space with different methods as branch and bound or branch and cut optimizations, where you can mathematically prove that large areas of the search space can be eliminated. And this way get a solution which is very fast, but also get assurances that you indeed traverse the whole relevant space and you get all the solutions or all the best optimal solutions. You also get simpler code. It's more generic. It's a generic approach, needing less handcrafting. And for me, I found like speed ups in 1 or 2 orders of magnitude and the problems that I worked on. The thing is that this is a new, for most of us, a new paradigm for programming. It's declarative. It's not procedural or imperative. We'll see example in a second. So you need to accept this maybe more strict and more verbose formulation. We still need some expertise to do the modeling, of course. But I think a lot of ML people maybe are not aware enough about this option, and I hope to convince you today this approach is worthwhile to at least to try for your next optimization tasks. So we will see most, I think, of these use patterns today, but essentially when we want to solve this kind of problem, it can mean find a solution any solution, like if the problem is feasible or not. We may want to find all solutions, but then again, maybe there are too many solutions, so this would not be realistic. We may want to find a solution that optimizes some kind of objective, like minimize or maximize, and find this optimal objective value. And we may want to find all solutions that suffice this optimized value, so all optimal solutions. And particularly in our tools, if you want to do this D, you first do a C, that is find the optimized objective, and then you do B, so you fix that found value, and then for that you can find all solutions. By the way, you would do a similar thing if you want to do multi-objective. And we should remember that we can also do things in Python. So if there are not too many solutions with no objective or with partial objective, you can just find them and then do some kind of post-processing filtering in Python just to keep the best ones. So I want to tell you today about a problem which I think is a beautiful problem. It's a non-textbook problem. For me, it's a real-world problem. I'm not sure if you will think the same. It's non-trivial, and I think it will demonstrate some usage patterns for CPStat and how to approach the solution, and like more general allow us to speak about modeling principles. So the original problem was, can any form like a diamond or pyramid contain all 26 letters? It was originally 26 because it was for English. I will discuss today 27 letters for Hebrew. And what they mean here, the writers, Philip Cohen and Ross Eckler from this problem published the WordWays challenge in 79, is can we put the letters into some geometric form so that the letters also form words or text, but in this specific geometric form. So for this, I need to tell you some things about Hebrew and about perfect pangrams. And the solution will be a 3D perfect pangram. What is a perfect pangram? A pangram is a text that contains all letters, and it's perfect if each letter in the alphabet appears exactly once. Now, Hebrew has 22 letters, and we can also take 5 final forms, which we have only for 5 letters, which gives us 27. Now, if we have 27, the idea is that we can put them maybe into a 3 by 3 by 3 cube and add the constraint that they form 27 words. So now we want 9 words in the X direction, 9 words in the Y direction, and 9 words in the Z direction. Now, there's some technicality that we will not be able to keep like the final forms in the end of words. So we need to relax this, and we will actually allow interchanging the final and regular forms for the letter that have those forms. I'll show this video later. So we have the issue of combinatorial explosion. There are many possible solutions to check. For example, if you look at letter permutations, you get 10 to the 26th. If you go at it in another way, you take some vocabulary of words and you look at word permutation. So you want to choose like 9 words out of this vocabulary and do different kinds of tests on them. You get even more possibilities. So it's too big to do exhaustive search. It will take more time than the age of the universe. So we need to be smarter about this. Now, what I mentioned didn't take into account symmetries of the problem of the cube itself. Symmetries are bad because it's redundant solutions that we would like to eliminate if we can. So for example, even if I choose some kind of axis system, I still have some residual symmetry left in the problem. For example, if I take these three words, Eyal ata ashaf, in Hebrew, Eyal, you're a wizard, you can still do 3D rotations and get the same solution, essentially. So we would like to eliminate this kind of symmetry. And here is the one, a very complex way to do it. Maybe we can constrain some of the letters so they can appear just in part of the cells of the cube. But it's actually quite difficult to get it right, and also it will not solve the complete symmetry. So and it's error prone. In this talk, we will use a simpler method. So let's go a bit into code and discuss the problem representation. So I suggest using 27 integer variables. These are for the cells, for each of the cells, and the value would be the like the Unicode value of the letter in the cell. Mind you, you could also go about this in a different way. You can consider the dual problem and having the variables represent the value of the Unicode value of the letter, and having their value represent the index of the cell. And in some problems, the dual representation might make more sense. But here, I think this is the easier way to look at it. So we first define these cell variables using new int var to create these variables. And I'm just using here two Python references, either as a flat list or as a cells dictionary with the location of the letters. Then I need 27 by 22 Boolean variables. This will be needed to do the counting. And they indicate for each cell if it contains the specific letter or not. So we just do model new bool var and add these Boolean variables in some kind of for loop. Now these both represent the same thing. We need to connect them together. This is called channeling, linking them with if and only if with implication constraints in both ways. So if the Boolean variables contain the specific character, I want the cell variable to contain in that index to contain that character, and if the Boolean variable is false, I want the cell variable to not contain that specific character. And this might seem overly verbose, but actually behind the scene it works like this anyway. So this is not an issue, and this is the way to go about solving it in this kind of CP sub formulation. Let's get to the main constraints of the problem. So, and this shows us the declarative paradigm. So for each letter, we want it to appear exactly once, instead of except for the final forms, which we said they can appear twice. So we add a constraint with model.add. The constraint is the Python expression, sum of the booleans should be equal to the allowed count, which is either 1 or 2. Then we want to check that the formed words, all 27, are actually from our vocabulary. And also for the optimization later, let's add some kind of score. The score would be the frequency of the words in our vocabulary, so we can get more popular, more useful words. So what I'm doing here, I'm just I need to like declare the variables for the scores, but then I want to add allowed assignments. So I take the first character in the row, the second in the row, and the third in the row, and the accompanying score, and I want to make sure that this combination is part of my list of words from the vocabulary. Now, I promised we will break the symmetry in a simple way. And for the sake of love, symmetry rating, and faster computation, I will choose the name of my girlfriend and just set like the middle word to be the 3 letters forming her name. In Hebrew, we have a lot of names in 3 letters, so it will work. Okay, so now we can go to the objective and solving the problem. So what I suggested is to maximize the popularity score of the least popular word used. So I don't want to have too strange words. So I want the strangest word or the rarest word used to still be as popular as possible. And the way to do it is define a variable for the score of that word and do add min equality. So the worst word, the rarest word, gets the lowest score from the words used, and I want to maximize that. So some kind of max min. And after I added the maximize objective, I just do solve or solve for the model. And this way I can get the optimal solution. And if I want to get all optimal solutions, I need to clear the objective with this function, add the found optimal bound as a new constraint to my model. So the worst I want it to be the score I found before, change the mode to enumerate all solutions, and then solve with some callback to collect these solutions. So there is a Google Colab. If you don't know about this, it's like a Jupyter notebook run on Google Cloud. The short link is tfee.la/or, like OTools. It's available. You can use it later and play with your own chosen name for your own sweetheart. It runs under 15 minutes, and we can quickly review it to see the how it looks like. So I just switched the share. Okay, so this is the Google Colab, and we need to start with the plan. So the attack plan of the battle station from the Princess Leia gave us this diagram of the cube, and we dissect it into 27 subcells. We put the letters inside, and of course the challenge will be to rearrange the letters in the orders so we get 27 words, 9 words in each dimension. This is not part of OTools, this is just some CSS I wrote. And essentially, I already shown you the important parts of the code. I'll go over this quickly. I install ORTools. I download my vocabulary. For Hebrew, I have a repo with Hebrew word list, so we will use that. We use Python, of course, to load the data and do some pre-processing. So to show you how it looks like, the most popular words are these short prepositions, like no, above, of, and so on. And these very rare words, which appear in the vocabulary only once. So the vocabulary is I crossed taking all the inflections from a dictionary with MC4 common core. So for each word, I have a score of the prevalence of that word. And these are like arcane third form feminine verbs. So probably we don't want this. Also, they are too long. So we need to filter the words. Again, this is just Python. I want just to keep the words that are 3 letters and either distinct or may have 2 of the same if there are one of those that have final forms. At the top one here are like he, she, I, but, and the third one are quite rare verb forms. Also, I limited the vocabulary to get, well, the first solution may take more time, but finding all solutions will be quicker. This is our tools. I set up the model and the solver after importing our tools. And essentially, this is the code I've shown you before in short form. I create the cell variables. I create the Boolean variables. I add the channeling constraints. I add the counting constraints. This is like synthetic sugar for instead of the sum being 1, add exactly 1. Just showing you some options for our tools. Adding the sweetheart name constraint. This is a bit verbose because I actually added the interface you can play with later. But in my case, just fixing these 3 letters to Yod, Ayin, and Lamed to form Yael. Adding the allowed assignment constraints with the allowed words and scores. So this is just the Unicode of the first, second, and third word in the vocabulary, letter of the word in the vocabulary, and the score. And now solving, either finding the feasible solution or finding the optimal solution. As I shown you before, here I'm just adding this logger callback. By the way, the feasible solution takes about 1 minute. This takes 8 minutes to find the optimum. And then if you want to find all optimal solutions, you just fix the bound, and this takes about 2 minutes. And most of the code is just a callback. And you can see I found 2 solutions. You can think about it as distinct or not, if you care about the word order or not. And this is the solution I got. We can stare at it for a second. And if you run it yourself, you will also get code like a URL, short URL, unique one, linking to your cube. You can see that the middle word here is the Yael. So let me quickly switch back to the presentation. Just to let you know, how do I do it? You can play with this later. So there are some resources here. I don't have time to go through them. You can see later some recommended references for OR tools, CPSAT, some other alternatives, more general frameworks that you can try different solvers, as the Minizink I mentioned before. You have here some links for dedicated solvers, specifically for a network or routing problems. Some of the offering also from all tools, and some interesting frontiers to look into in automatic constraint acquisition, into explaining the found solution or fixing relaxing solutions that you couldn't get all constraints satisfied. And also some people are working on stuff with LLMs. I think it's still early stage, but it's interesting to follow. Yeah, so this will be shared with you later, and I'm happy maybe we can take 1 or 2 questions if we have time.
I mean, that was great. And I think we are unfortunately at time as we speak. So I think we will wrap. But I do invite folks, if they would like to continue or ask questions, to head over to Discord. That link is in the reception area. And I want to thank you again for presenting. Thank you so much. And we'll see everyone at the next PyData Global session.
Thank you very much.